All right, so we are going to go through this Bellwork. And first, let's look at the problem. We're basically doing something similar to what we did the other day. Again, now we're solving with a different set of data points, right? The other day we played make-believe that we were on the moon. What would that influence? How would we redraw a graph? Today we have the graph, but this is different than the graph we had. We're on a different planet, and in this case we're robots, right? So let's look at the hint. First things first, find some data points and solve the equation on page 15 for A. So let's think about what that means. So what is our equation on page 15? Now the other day we solved this for t. You recall this? Yeah. We did the algebra and we solved this for t. Well, this time we're going to solve it for A because that's what we're after in this question. So to solve this for A, first I'm going to get rid of the 2, or the 1/2. Multiply both sides by 2, right? So 2d equals AT squared. What am I trying to get by itself? A. How do I get rid of something multiplied by something in a fraction, in a equation? Divide it. So to clean this up, A equals, right, this is going to cancel. So A equals 2d over t squared. So now I have an equation for A. What's next? Plug in. We need some data points, right? You have this graph in front of you. You need to select some data points. And again, from your notes, we kind of did this as well, right? We had D and T, and we filled in a chart. Now, when we were building a graph, we had to fill in 4 or 5 different points here, right? Well, we already have the graph. So we need to pick several of these points, right? So I see that the points line up. Now, I drew some points on here. That's how I drew this graph. But you could pick any point on this line that lines up with anything you want, right? I'm going to pick the point that is above, I don't know, 0.010 seconds. What does that point look like it is? Who can interpret that? What's the distance that matches up with 0.010 on the time on the bottom? 1.2? 1.1, 1.2, I agree with that. So that's 1.2. What was the unit? Millimeters. Let's pick another point while we're doing this. Let's pick the point above 0.020. Let's do 0.025 for the sake of doing this. What's that point, do you think? 7.2? Okay, so 7.2. So now we have some points. Now again, per the Bellwork, what units do we want to solve for A? What's the unit going to be? Not seconds. This was in the Bellwork. Let's go back. Meters per second squared. So am I going to have a problem if I just dump this data in? Yeah, what do I need to do first? Yeah, I need to convert. I've got a distance here in millimeters. Is that going to help me? Well, help, yes, but is that the number we need? No. So let's convert this into meters. How do we do that? T-chart, yes. And I know because it's millimeters, I'm going to move the decimal 3 places and get 0.0012 and 0.0072 meters. Right? This is all just kind of steps. Right? To go somewhere in your car, you need to know what roads to follow. And that's kind of what these problems are. Right? I need a data chart. Do I need the data? Do I have to follow the points? Solve the equation? Do some conversions? All of these are just steps. And albeit you need to kind of know what those steps are, and that's why we've done several of these problems so far in class. We did the lab, we did the Bellwork the other day, and now we're doing this. So now I have values for D in meters, and I have values for T in seconds. Now I can solve my equation. So for this first line, I will plug this in. 2 times 0.0012 divided by 0.010 squared. And for A, I guess we'll call this A1 for A2. I have 2 times, what was my value for D? Was 0.0072 divided by T for this one is 0.025 squared. Right, now I'm just plugging the points in. I'm plugging in the points on this line first, line 1, into here. And I'm plugging in this point, point 2, in for A2. Somebody got a calculator? I don't know where my calculator is. So, oh, sorry, I'm in the way. So let's plug in for A1. I get 2 times 0.0012 divided by 0.01 squared. 0.0012 divided by 0.01 squared. I get 24. And then for A2, 2 times 0.0072 divided by 0.025 squared. I'm just going to leave it at 23. So now I have two numbers. Why did I do this for 2 data points? Yeah, right? How much accuracy do we have right now when we're kind of guessing at where that line follows across? Is that a lot of accuracy or a little? A little. This is a small little bitty graph that I gave you, right, without a straight edge or something else. I just kind of made a best guess at that point. And you could do this for many different points across this thing. We could find where it crossed lines or whatever. We're just kind of taking a best guess based on this graph. So I might take an A3 or an A4 based on the points here and kind of average those numbers out. Right? But that gets me my value for A. So let's keep going. This is physics, right? If we're going to accept a value of, say, 23.5 meters per second squared is the A on some planet, what does that mean? Acceleration. So what does that mean if we went to planet Kepler 22b? What's the acceleration here again? Gravity. What's the number that we use for here? No? It's on page 15. It's in there.
980 centimeters per second.
Yes, so our number in meters would be 9.8.
Yeah. So it's faster.
So, it's more. So how would we feel on Kepler 22b? We'd feel heavy. Yes, that'd be like being in the gravitron or whatever you call it at the fair, where it presses you against the wall. This is over twice our normal gravity. Right? What was the number for the moon? You guys remember? 1.625, I think is what we said, or 1.63 or whatever it was. That was less gravity. So this is over double our normal gravity. That's kind of what this means. Right? What about these robots? Look at your data. How's their reaction time? Faster or slower than ours? Like a lot faster, right? They're robots, for crying out loud. So why did they use a different measuring system? What did we measure our distances in? Remember when we did the lab? What did we measure in? Centimeters. Why did the robots use millimeters? Yeah, they got a super fast reaction time. These are robots we're talking about, right? Even though the gravity is more, like there's a lot more gravity on that planet, so that thing is going to fall faster. We're talking about robots. They got really fast reaction time, so we measured that number in millimeters. They're robots. They can do that kind of thing. Anybody thoroughly confused by this stuff? So these are all just, these are kind of like big T-charts. Remember the big T-charts at the end of chem last year, the stoic T-charts, where you had like 10 boxes across? You guys all loved those? Love me some giant T-charts. This is kind of similar, where you have a complex problem. You have some things you need to look up or whatever. But each one of these little steps shouldn't be that difficult. Solving an equation for a variable, it's just algebra. Picking some points on a graph, that's just following your finger across and seeing where the points are. Plugging some values into an equation, man, that's easy. You just substitute a number for the letter. None of this should be terribly intimidating or difficult. So let's keep going. What did we do yesterday? Yeah, so we measured stuff in the hallway. Now your homework last night was to read the physics talk, read the chapter. What were some of the words, some of the things that were in that physics talk?
Can we go over like question 8, like and 9, because, or question 9, because that did not make sense at all.
Sure, but we're going to wait a few minutes and then I will go over that. That's fine. So in your notes, so in your notebooks, in your notes, there should be a section in there for the physics talk, and I want you to put in there all of the physics words from this section. Words like accuracy and precision. What were the other ones? Systematic errors, random errors. In your notes, all of those words need to be there. That's part of the physics talk. When it says physics talk in this class, that's what I want you doing, is reading through the vocab, putting the vocab words in the thing, taking notes when we go over it like today. But that's what I'm talking about when I say read the chapter. So let's talk about, so you're not writing that words now. We're doing the lecture now, so hang tight. If you didn't do that before, you'll have some time after I get done. So let's talk about the thing we did yesterday. How'd it go? How accurate were we using strides to measure the distance on the floor? Not very. Any other? Guys, I'm going to want you up here, not having separate conversations. So how accurate were we with strides? How can you tell not super accurate? I agree, but how can we tell? Yeah, look on the board. Right, our low number was what? 7.8. Our high number was, in this class, 1602. There was another class that had like 21 or something ridiculous. Why are those numbers so different? Is that what made the difference? Is the difference in strides what caused the difference in values here? No, why not?
Because not everybody measure from the same point.
True, but why does it not matter that my legs are longer and my strides would be longer than yours? Why does that ultimately not matter? Why could we still get to the right number? No, not faster, because it's just your stride. Whether you did it in 10 seconds or 20, it had nothing to do with time. It had to do with how far your strides were, yes?
It's the same distance.
Yeah, it's the same distance. So you're right. Your stride is shorter than mine, but you would take more strides. And that should work out in the math, right? If it's 10-meter difference and my strides are 1 meter, I'm going to take 10 strides. If your strides are half a meter, you're going to take 20 strides. But ultimately, we would both arrive at 10. So why the variance? It wasn't that. It wasn't that some people's legs were shorter or longer. Why the variance? Somebody said it. How did you measure your stride?
Like that. I'm saying that's not. I didn't say like shorter
some
or
people
longer.
start
I said
from,
some people start from like the heels.
Oh, okay. Yeah, so you're right. How do we measure a stride? Is it from the back of one heel to the front toe of the other? Is it from the middle of the shoe to the other shoe? Is it from the tip of the toe to the tip of the other toe? All of you measured it differently, and many of you asked, like, hey, how do I measure stride? And guess what I said?
Figure it out.
Yeah, figure it out. I don't know. And truly, I don't. Like, if you've taken anatomy, I'm sure Miss Z would tell you, hey, here's how we measure stride of an animal or whatever. I don't know what that is. I don't do biology or anatomy. But I know you all did different things. Here's another thing. Look at your data right now for yesterday. Who had a number of strides that was not a whole number? Who had a number of strides that was like 17.5? Any of you? So now wait. If this is the finish line and I'm taking strides, right? 17, 18, 19. Is it really 19 strides? Well, how would I maybe measure this? 18 and a half. None of you had a decimal in your number of strides, but should you? Yeah, probably, right? If you end here, here, and then here, what's that? Is that 3/4 of a stride? Is that, and again, we didn't really say what exactly a stride was. Never did I define it. And all of you kind of did your own thing, but I found it odd that across 4 classes and almost 40 groups of students, no one had a decimal for strides. And I watched. Groups would end here, groups would end here. There was all sorts of different, like, crossing the finish line kind of things, but nobody did a fraction of a stride. So what would that cause? An inaccuracy, an error. What about, was I specific about, look, how wide is that line out there? How wide is the lines of tape themselves? Did anybody measure that? Maybe an inch, a couple centimeters, because science, right? Did I say measure from the inside of the tape to the inside of the tape, or the beginning of the tape to the beginning of the tape, or outside to outside? Did I specify? Tape to tape. What does that mean? Right? Does that mean the starting point of the tape? I mean, the tape had a width, right? And would that impact your measurement? For sure. We're going to do a ton of measuring stuff in this class, and that's why this second lab we did is all about measuring stuff. Right? I saw some groups, they trimmed it when they got in here. They had like 4 or 5 decimal places listed in their notes. Right? Can you have that much precision with this kind of measuring? No, no way at all. Right? There was a lot of error in what we did. Some were systematic errors. Some were counting errors. There were all sorts of errors in what we did. And ultimately, if we really wanted to measure the distance between that tape out there, would this be part of the solution? No, ideally not. But this is evidence of what we're going to do. We're going to be doing a lot of measuring in this class. We're going to use yardsticks and meter sticks. We're going to use rulers. We're going to use the tape measure. You're going to use stopwatches or on your phone. And we've already seen, how's our reaction time on that sort of thing? Not good. Right? So all of these are going to be errors in our measurement. And what this chapter is all about is kind of trying to think about that thing. When we're measuring something, whether we're using a scale or using a meter stick or using a stopwatch or the timer on our phone, there's always going to be some kind of inherent inaccuracy. And in physics, we need to kind of think about that. Like, how accurate are our numbers? Why were the numbers for using the meter stick so much better? So much of a tighter spread versus the strides. Why is that such a better method, I guess we would say? What did that kind of take out of this? What errors did that reduce?
Less distance from the tape, like the tape width is a less distance than like your whole foot to where your feet.
Sure, yeah, yes. So again, part of this is method. How will we measure a thing? Right? What kind of tool would we use based on whatever it is we're trying to measure? Right? And that's what some of the questions are that are in here. There's an interesting exploration on, I forget, no I don't, on page 29, where it goes through measuring something like an Olympic swimming pool. right? And if you think about doing 30 laps in an Olympic pool for, I think, the 1500, you go back and forth 30 times, right? What would happen if the width of that pool is off by just a little bit? Right? It's supposed to be 50 meters, 50.0 meters, right? How did they measure that? Hopefully with a laser or some other kind of very precise device, right? But how would that affect Olympic times? If it's off by just a little bit and you do 30 laps, why would that be a big deal? Sure, yeah. Think about that. What was the one race? I think it was the 100 meter or the 200 meter that the difference was like 5,000ths of a second or something. The photo finish thing where one guy's, his torso crossed like 5,000ths of a second faster than the other guy, and that was the difference between gold and silver. Right? So that makes a big deal in something like the Olympics, where we're talking about the best athletes in the world swimming or running or whatever it is as fast as they can. Wouldn't you like to know how accurate something is? And you really want to be accurate at the Olympics, right? But how accurate can you be? Can you ever be very exact no matter what you use or what device, right? It's all just best guess and using the best tool for the job. And I would guess they do laser sighting and all sorts of fancy things to get that right at the Olympics. But, you know, could they have done that 10, 20, 50 years ago? No, it's just some guy out there with a tape measure probably. So that's this chapter. That's what this chapter is talking about, measurement, because we're going to do this all throughout the rest of time. Right? So homework today, you have plenty of time in class to work on this. The assignment is also in your Chromebook, but it's basically read the physics talk, do that. The APP questions, they're the ones in the blue. On page 29, there's some questions in there to answer. And then also the physics to go. I'm going to check logbooks tomorrow. I forget. I think I have the page listed somewhere. 32. If you still have questions on what we did for Bellwork, please come up and see me.